So can we start? I think we are more or less all here. So do you remember yesterday we started discussing a little bit on the usage of H over V? And we came to the point that since H over V is in some way related with the shape of a ratio, it's related to the underground structure, one could try to retrieve information of the underground structure directly by inverting the H over V. So looking for the model that would be able to reproduce the H over V that is observed in the field. But I told you, and I show you an example where the H over V, also for two different models, as an example, can show exactly the same shape. And this is related mainly to the problem of trade-off. So the fact that changing the velocity in one layer and accordingly the thickness in the sedimentary layer, this could lead to a very similar H over V. So if one wants to have a reasonable estimation of the underground velocity profile using the H over V inversion, should at least have some independent information either on the thickness of a sedimentary cover layer or on the velocity profile. So till here, it's all clear from yesterday. Can I go ahead?
Yes.
Okay. So this is one of important point. The other important point that we will see here is that the H over V can be also strongly affected by the influence of different modes and also by the influence of the presence of low waves, at least, if we consider the wave field as mainly dominated by surface waves. Here you have some example of different velocities profile. You see are quite old examples, just to show that the problem also the influence of different modes of the composition of importance of the composition of the wave field is nothing really new, but it's something that it has been studied very deeply already in the last 30 years by scientists. Here you have different velocity profiles. You see the first one to the left with a clear velocity inversion around 60 meters. Then you have a velocity profile with a shallow high velocity impedance contrast, a velocity profile with an increase, gradual velocity with depth, and then a very complicated velocity profiles where you have an alternance of layers with very large velocity, also inversion, increase and decrease. How this can affect the H over V. So just keep in mind the velocity profile A, where you have a deep velocity inversion, and the velocity profile G, where you have a very clear velocity inversion at different levels, a shallow one and deep ones. So the observed H over V is the one where you have these crosses. So this is what we calculate in the field, from the data in the field. You see that in the case of A, so this is period, so if we see it as seismologists, generally we look more at the frequency, you have to turn it in the other direction. So this profile is showing mainly a low frequency fundamental frequency that you can observe. It's mainly related probably at the impedance contrast here, but also some complicated shape of a profile. The dashed line is the H over V if we only consider the fundamental mode of Rayleigh waves. If we are considering also more modes, also higher modes that are generated in the propagation. Shoaib, who is here, is a specialist in this. Due to the polarization of the higher modes, you see immediately that the shape of H of AV, which is this black line, is becoming more similar to the shape of H of AV that was recorded in the field. And especially you see that the peak, that also by theory should tend to infinitive for the fundamental mode, is not going to infinitive anymore. And this is due to the presence in principle of energy in this frequency range due to the higher modes, especially of the first mode. This we can see it here. This is just, you can imagine as a sort of the spectrum, let's say, the spectrum of a vertical component at different frequencies. If you look at the fundamental mode that is with this dashed line, you see that as we expected with theory, due to the impedance contrast, the amplitude of a vertical motion of a fundamental mode is going to 0. And that's why if we consider in the H over V only the fundamental mode, we will have a peak tending to infinitive. But at the same frequency, there is some energy on the vertical component coming from the higher modes, from the first higher mode. So this energy is the responsible of the fact that the H over V ratio is not tending to infinitive anymore, but is becoming with a certain finite amplitude, which is much smaller, a little bit larger than 2, or between 2 and 3 in this case. A similar thing is happening also if we consider the more complicated velocity profiles with several inversion of velocities. These inversion of velocity in some way are, let's say, facilitating the propagation and the generation of higher modes. If we would look only at the fundamental mode, again here, we see that we have, due to the two large impedance contrast with inversion of velocities, we would have two clear peaks in the H over V that you see here from the dashed line. But we see only nearly one peak in the
hello,
in the H over
Professor.
V. Yes.
Inversion of velocity means the perturbation of velocities at different depths.
I mean, this case here, in G, when you go with depth, you have first an increase of velocity, then you have a lower velocity layer, and then it increases again and so on, okay? So you have a very large change in the velocity with a large impedance contrast in depth.
Okay.
Okay?
Okay.
So what you see here then is that if I would analyze only the fundamental mode, I would have clearly two peaks, while in the, let's say, observed spectral rates, I have nearly one peak, mainly in the higher frequency part. The low frequency peak is nearly masked. If I start including also the effect due to the energy of the higher modes, so we can understand why this peak is nearly disappearing. So the black line is considering again the effect at least of the first mode, of the higher second mode, and you see that they can have some important amplitude also in this frequency range where I would have had a trough, let's say, in the fundamental mode. So the first mode has some significant energy in the vertical component, and that's why the H over V is not so strongly peaked. If we want to get even closer, we can also include the effect of love waves, because we cannot exclude, like we said yesterday, that in the full wave field, we have also a contribution of love waves. So you see that when we include also the love waves, the H over V at the fourth site, here I am reporting, before we were looking only site A and site G, you see that the fit of the h over v curve, the theoretical one, with respect to the observed data is even increasing even more. So it's quite clear that when we want to consider the h over v that we observe in the field, we have to consider, only when we want to explain it, we have to consider a sort of full wave field, at least for the surface waves. And we cannot exclude that in some frequency band, still some body waves can have some importance in the shaping of the h over v. So if we now know this, we know how to generate a theoretical h over v, and that we saw that considering both love waves and Rayleigh waves and higher modes, we can reasonably fit the observed ones, then we could also try to use it in an inversion procedure. And in principle, we can make an inversion. I indicate here, for example, genetic algorithm as a nonlinear inversion tool that is minimizing the difference between the observed h over v and the calculated h over v. So we can minimize this difference until when we found the best model that is able to reproduce the h over v more. So now I have a question before proceeding. If you have some ideas of how the inversion is working. Not at all?
Yes.
No or yes? You have an idea?
No
idea. Okay.
Yes.
I will, before going on, then I will make you just an example of what I'm talking about in order that then we will repeat it again and it will become even more clear. But I prefer to say it twice in order to make it clear and clear. So, sorry, I have to skip a lot of slides then, but I think it's good to introduce it, just to give you an idea of what we are talking about. So when I talk about forward modeling, because this point will come many times again, and we will see it again. But first idea is, when we talk about forward modeling, we talk about, okay, I can make a model, for example, of an underground structure. And for this model of the underground, I can simulate a source, and I want to calculate the synthetic, for example, seismogram that due to a source here, I would record at a station somewhere here. So this is my forward modeling. So given the description of the model, given some, let's say, physical and mathematical laws that are linking the generation of waves and their propagation, I can generate some, for example, synthetic seismograms. Or I can generate some synthetic H over V. Or I can generate some synthetic dispersion curves, for example. When I talk about inversion, I don't know, for example, what is my model of the underground. I have no idea, but I have recordings at these stations, which are at the surface. So from this recording, I want to estimate information about the structure of the underground. So this is my inversion or my inverse problem. So I start from the observation and I try to find the model who is better able to reproduce these synthetic seismograms. Okay? Of course, the two things are going together because if I want to find the model that is better able to generate this observed seismogram in some way, I have been also able to calculate seismograms for a given model with certain parameterization and to change the model's parameters until the seismograms that I generate are more close or more similar to the observed ones. Okay? This is in principle. Let's see a simple example of a for example, or the linearizing inversion that we can attempt. So just imagine we want to study the velocity of this block. We can imagine this is just a concrete block, no? What we can do? We can go by one side of the block. We can generate some waves, no, with a source. So we just generate a pulse. And we have a sensor by the other side, like here, which is receiving the signal generated by that source. Okay? For sake of facility, we will divide this block in a certain amount of blocks. So let's say 4 blocks with the same dimension in the horizontal and in the vertical direction. Just imagine we work on a slide. Don't think in 3D now, just think on in 2D. Okay, so for each of these sources, we know when we shot, and we can measure the signal when we receive it. So we can have an estimation of a travel time from the source to the receiver. So what we want to measure? I have a block. I would like to see what is the structure of velocity inside my concrete. Let's say this is a dishomogeneous concrete block. So I don't know anything. I'm just outside, and I will shot by one side and measure the velocity, the travel time by the other side. Okay. So H is just the theoretical, let's say, dimension of each one of these blocks, smaller blocks in which I subdivide the whole mass, let's say, the whole cube. So if I shot in this place and I record in this place, I can say that this first travel time that I call T1 will be equal to what? Will be equal to H, which is the horizontal distance in the block 1, divided the velocity, so the travel time in the first block, plus the travel time in the second block, plus the travel time in the third block, plus the travel time in the fourth block. So I can write it in this way. The slowness is nothing else but 1 divided the velocity. So here I'm just dividing the path, h, for the velocity in each block. So it's just the sum of a travel time in each one of these blocks. So this is my first datum. Then I move to the second block. I shot again, and I can write that the second travel time is equal to what? It's equal to h multiplied the slowness in the 5th block, h multiplied the slowness in the 6th block, in the 7th, and in the 8th block. I do it for all the 4th direction in this year, in this in the horizontal direction, and then I start shooting in the vertical direction. So my last shot, the number 8, so I will have 1, 2, 3, 4 horizontal shot, and then 5, 6, 7, and the number 8 in the vertical direction. In this case, the travel time from here, from the top to the bottom, will be equal to h multiplied s4 plus h multiplied s8 plus h multiplied the slowness in the 12th block plus h multiplied the slowness in the 6th block. So at the end, what I get is simply a system of linear equation. And I can rewrite this in form of vectors and metrics. So I will have a vector of data, which are my travel time, a matrix which is describing the linking between the travel time of each ray and the slowness in each block, but it's a matrix with 1 in the position of a block that are sampled and zeros in the blocks that are not sampled. So you can see it here from TH. I will have a 1 in the block 4, in the block 8, in the block 12, in the block 16. And then it's simply multiplied for a factor h because this is identical in each block, because the dimension horizontal and vertical is the same. So this is the matrix that is linking my data to my unknown. And what are the unknown in this case, what I want to calculate? Oh, these are simply the slowness and therefore the velocity in each one of these blocks. I can then make any linear inversion of this system to calculate my unknown. Okay? This is if everything is linear. What is the problem? The problem is that if my blocks have different velocities, the first arrival that I use to measure the velocity might not be the wave that is propagating in the horizontal direction in this case. But maybe it's a wave that is making a little bit longer path, but in blocks with higher velocities, and therefore is sampling our model in a different way. So the problem is that also the path that we have depends on the velocity. So we have a nonlinear problem. So if a problem is linear, so every time that we assume a model for starting my inversion and then modifying the parameters until I find a good fit, I mean, every time that I will adjust the model parameters, you see here, my solution, SM, is just the misfit between the solution that I found and the observed data. This misfit is decreasing continuously until I found a local minimum of the solution. So independent on the model that I will use to start the inversion, I will converge to a model, to the, let's say, around the best model. If the problem is nonlinear, like the case we have seen before, the space of the solution here, the misfit between the observed data and the retrieved data from the model can be more complicated with many local minima. So if I make a linear inversion, like we have seen before, starting from a wrong model, for example, a model that is here with these characteristics, when I proceed with inversion, I will converge, I will arrive to the local minimum, but I will not be able to escape anymore. So in general, to solve this nonlinear problem, nonlinear tools, let's say, inversion methods, must be used. And there are many different ways for doing also nonlinear inversion that are just playing a little bit from what is the optimization and the exploration. So in the optimization, let's say exploitation, we try to have a fast, let's say, convergence without exploring too many models. The risk is that when they are too much, let's say, exploiting the data, we are risking not to investigate enough space of the solution. Or we can have methods that are exploring a very large space of a solution. So they test many models, but the risk is that, of course, the convergency or the calculation time can be a way too long. So in general, there are some methods like simulated annealing or genetic algorithms or neighboring algorithms that have some compromise between a uniform search that can be very time consuming and heavy by the calculation point of view, and methods that can converge, let's say, too fast and maybe are not exploring too many models and have a risk to stick in a minimum, local minimum of the solution. I give you just maybe an example for the calculation of a dispersion curve. We didn't reach yet this point, but we know that when Rayleigh waves, for example, are propagating, we can measure them, and we can measure also their velocity, what we call phase velocity. We discussed it in the first lecture. So we know that different frequencies of Rayleigh waves depending on the underground model, they can show different velocity of propagation. So given this curve that is showing how Rayleigh waves, which velocity they are propagating, we look for the model of the underground that is able to reproduce this curve. So here you have an example for dispersion curve, but the same could apply also for the h over v curve. So given an h over v curve, I can look for the model of the underground who is able to reproduce this curve. So in the case of a dispersion curve, what are my observations? My observations are the phase velocity, so this data point that I measure. So the phase velocity at each frequency of the surface waves. What is my unknown? Okay, if I start from a certain guess, a first model of the underground structure, I will look for the changes in the velocity that I have to make to the starting model in order that the curve, the theoretical h over v curve, will fit this observed curve. So I will start from the model and I will change it step by step until it is able to reproduce a dispersion curve similar to the observed one. What is the link between the observed phase velocity of the changes in it and the changes in the velocity in the underground from my original model? It's a Jacobian matrix that you see here. It's a matrix that is linking the changes in the phase velocity of each frequency to the change in the velocity of each layer. So in principle, these partial derivatives is just telling me how much the velocity, the phase velocity here of the first frequency is changing if I change the shear wave velocity in the first layer. This last column is telling me how much the phase velocity of the first frequency, you know it's always omega 1, is changing if I change the velocity in the bottom layer. Similarly, the last line is telling me how much the phase velocity of the highest frequency here is changing if I change the velocity in the first layer. And in the last column, how much the velocity, the phase velocity of the highest frequency here is changing if I change the velocity in the deepest layer. So this Jacobian matrix is giving you the link between phase velocity and the changes in the shear wave velocity in the underground. So in this case, we can linearize, for example, the problem, once again, where I have a vector, which is my observation. In reality, my observation, like the travel time before, are the difference between the observed velocity, phase velocity, and the one that I can calculate for a starting model of the underground, that I can just guess. Then I will have a matrix J, that is the matrix I described before, where you have a number E of rows and a number J of column, which are the unknown. So I will have as many J, as many layers I have. So if I'm inverting for the velocity of the layer, and the rows will be simply the number of data, the number of frequency of my dispersion or H over V curve. My unknown is the update of the velocity in each layer. And this I can do it with some methods like singular value decomposition. Just to make it again more clear, how can I calculate these elements, my datum? Again, I repeat, this can be, it's a dispersion curve, but can be an H over V. Okay, I just define a starting model, which is reasonable based on the previous information. And for this starting model, I can calculate a theoretical curve. So you see, for example, the blue curve. And we immediately see that the blue curve is not fitting the gray curve of the observation. There are differences. Okay, for each frequency, I calculate the differences. And these are my data, my observation. Now my task is to reduce these differences, changing the velocity in each layer until this blue curve is becoming more and more similar to the gray one. So to do this, I told I need to calculate a matrix, the Jacobian matrix, that is linking the changes in the phase velocity to the changes in the underground structure, in the shear velocity in each layer. So how can we do it? Thinking in a simple way. Okay, I have my starting model. What I can do, I just change the velocity in the first model. So I calculate my delta Vs, a change in the shear wave velocity. For this model, for this new model, I can calculate a new theoretical curve. And again, for each frequency, I have a difference between the new curve and the original curve from the previous model. So this difference is telling me exactly how much, given a certain velocity change in a layer, my phase velocity is modified. So you see automatically, numerically, you are calculating this first derivative. So if you do this for all the frequencies, you see in this diagram, you will see that for the first layer, how much the velocity is changing depending on the frequency. Then you can do the same for the second layer. You calculate again the dispersion curve, you compare it with the original one, and you have again, given a changes of velocity, this time in the second layer, how much the phase velocity is changing. And you will get something like this. And so on, you do it for all the layers. So this is nothing else but the matrix that we said before as a function of the layers. You see here, I also indicate the depth that for this model, as an example, these 5 layers were 1, 2, 3, 4, 5, 6 layers, sorry, were exploring or describing. And this is telling you how much a change of velocity in this layer would modify the phase velocity of the different frequencies, which are on the x-axis. So what you notice, for example, is that a change in the shallow layer will modify, in particularly strong high frequency. When we go to the deep layer, a change in the velocity in the deepest layer is not affecting, you see you have white here, the high frequency range. It is only seen, let's say, by the low frequency. And this is obvious because we said that the wavelength depend, and the depth of investigation, they depend on the velocity divided the frequency. So only the low velocity, the low frequency have long wavelengths, and so a lot of depth of penetration, and only they are affected by the changes in the deepest layers. So generally, when you do this, you can then invert to obtain a solution using many methods like a singular value decomposition and so on, other tools. And what you are generally doing, you start from different models. Since we said it's a nonlinear problem, we try to linearize it in this way. So we could have a risk to end up with our solution in a local minimum and not in the final minimum. So we start from different models, like all these black line. We solve the problem and generally we obtain a bunch of models like this one. What is telling you this solution when the models starting from different models are collapsing? Okay, we can say that in this part we trust the solution because all the models are narrowing amongst very similar values. For the deepest part, that is also less constrained by the frequency, you see that the solution is not converging too much, so it's not very well constrained. Okay, so this is if we use a linear approach for the inversion. But as we said,
Hello, Professor.
yes,
Uh, I was wondering that how can we, I mean, the number of layers or the thickness of the layers, does it only depends on the literature or the previous
no,
information?
no, you should fix it. There are some good points. So as I mentioned, for example, you have a dispersion curve here. I go back, sorry, just to show you one. We mentioned that the wavelength depends on velocity divided frequency. And the depth of penetration, let's say, it's nearly the wavelength divided 2, wavelength divided 3. Depends on the model, but this is just roughly speaking. So it means that if I have here 5 hertz and 300 meter per second of velocity, the wavelength of the signal will be around 60 meters. So in general, this signal will propagate, since we said lambda divided 2, wavelength divided 2, in the uppermost 30 meters. So I would say that makes no sense to have layers thinner than 30 meters in your inversion, because your wavelength is not able to discriminate the velocity changes within these 30 meters. It just sees everything like a sort of average velocity. Okay? So it makes no sense to have a smaller layer. If you do it, of course, you will get a result of inversion, but you don't have a resolution enough to be able to do it. It's just a sort of numerical artifact, let's say, of your inversion. What is the deepest layer? The deepest layer depends again on the wavelength. So here we have, let's say, 1000 meter, 1 hertz. So we have a wavelength of 1 kilometer. So it means we can investigate down to nearly 500 meters, more or less. So the model should be subdivided in layers, starting from a first layer of 30 meters and reaching a depth of, let's say, nearly 500 meters, not more. So in this range. Otherwise, you know that you don't have waves going enough deep to be able to see what is below. Okay?
Yeah.
This is just to give you the range. One way where you very simple, a very simple trick to have a sort of first estimation of this layering is also to transform this curve not as a function of velocity, of phase velocity and of frequency, but as a function of depth and sort of shear wave velocity. So this is obtained very easily, simply dividing the frequency, like we have done, the velocity for the frequency. So you will obtain a sort of wavelength, you divide it for 2, and you can plot this value of the velocity adjusted for the ratio between velocity of Rayleigh wave and shear waves, which is 0.5, something small, as a function of depth. So you will have a sort of profile, velocity profile versus depth that you can use just to define the main changes in velocity that you can put in the starting model. Okay? Is it clear?
Yeah, but if we are not sure about the thickness of the velocity, so we need to run the multiple inversion with the variable thickness of the layers.
Of course. Generally, you invert both for thickness and for velocity. So you leave the possibility also to the layer thickness to change. Here I'm just showing you for simplicity, just the dependency only on the velocity. So I assume here that the thickness is fixed, let's say, and I only invert on the velocity, just to show you this effect. But exactly what you observe here for the velocity, it's also valid for the thickness of a layer. So in this case, you would not change the velocity, but you would change the thickness of a layer, and you will watch at the changes in the phase velocity due to the change in the thickness of a layer. So in our matrix here, we will have more column because the solution will not be only the adjustment of the velocity, but would be also the adjustment in the thickness of the layer. So you can put all, okay?
Okay.
So this depends. I only fix it here as an example to keep it simple. But if you would have more parameters, you would repeat the same for all the parameters that you are considering. Okay?
Okay, thank you.
So this is if it's linear. I will introduce you also shortly something about nonlinear optimization, and in particular, because personally it's one of the methods I'm using more, for example, the use of genetic algorithm in solving this kind of problem. So what is the difference here? In this case, we are not having a matrix inversion, but we just have an optimization procedure. So what we do first? Generally, we generate randomly a certain number of models. So here, for example, I'm saying 30 models within a certain range of velocity for each layer, and also, like you said before, in a certain range of thickness. So this is just randomly done. We generate, for example, 30 models like this one. Each model is described in a binary form. For example, the velocity of each layer, in this case could be 149 meters per second, is described in the binary form. So I'm just using simple binary form in which I have 1 and zeros, depending on the power of 2, in order to describe this number. I do it for the velocity in the first layer, then I add another part of this describing the thickness of a layer, then another part describing the velocity in the second layer, and so on. So at the end, the description of a model is made by a series of binary numbers with a binary representation. And so it's a sort, this is our gene, let's say, describing the model, sort of ones and zeros following each other. Okay, for each one of these models that I described in this way, I calculate a dispersion curve, a theoretical one. So just imagine these are the blue curve that are describing, that are the dispersion curve, or can be the H over V, for each one of these black models. You see that some of the models are closer to the observed curve, some of the models are more far away. So I assume that the models that are producing a curve which is closer to the red one are better models, because they produce a curve which is already quite close to what is my observation. So I'm assuming that I describe the quality of a model, the goodness of a model, on the basis of its fitness to the observed data. So I have a sort of fitness function that I will define to describe how good is a model. And my fitness function, for example, my misfit function can be just simply the difference between the observed data and the theoretical one. Here is divided on the standard deviation if you have an error in your observation for each frequency. So for each frequency, I calculate the distance between the theoretical curve for each model and the observed one. I just sum them, the square of them, and I just normalize it. This is my Misfit function. So smaller will be this number, phi, better will be my model. Using this information, I can also describe a fit function, which is 1 divided the misfit. So I will have higher values of f for a model when it's fitting best the data. Okay? So, but now I have to modify these models in order to test new ones, hoping that they are even better than the one I found here. And how can I modify them? Generally, they are modified considering the probability of a model to be reproduced or to have some part of itself to be reproducing a new generation. So generally what we give more chance to be reproduced to models who have a higher fitness. In general, we define then a probability for each model to be reproduced, and the probability is nothing else but the ratio between its fitness and the total fitness of all the models that I calculate in each generation. So the model that have higher F will have higher probability with respect to the models that have smaller F. Okay, I will fish more the characteristic of these models in future. And generally, for example, here, these green models, you see that are the closest one to the observed data are the ones that are a little bit more clustering around certain values of a velocity profile. But how to change then this model, how to generate new models? This is done using what we call genetic operations. And there are mainly two genetic operations, at least what we use in this algorithm, that are called crossover and mutation. And generally, they are applied to the models, depending on the probability, and then a new generation of model, a new population of other 30 model is generated and reproduced. So how these operations are working, why we need this gene in this binary form, because applying this operation in the binary form is quite easy. So the crossover operation is made to combine randomly features that are belonging to two models that are selected. So depending on the probability, I fish from my model distribution, the models depending on the probability of being reproduced. And then between the model, I can exchange different parts of their gene. You see, for example, I fix to exchange this part of a gene. So this part of the top model will go in the bottom model and vice versa. So I start mixing the model in this way. Of course, I can do it selecting randomly more points of a gene and so on. The mutation is using each gene separately. So it's not combining the two models, but is modifying one of the models that I fish, and then is just making a mutation in his genetic code. So, and this is just randomly varying a bit in its genetic code. So you see here, what is happening is that there is a flip of these, you see, values that is becoming 1 and 0, and the rest can also be modified, for example, here, if this position is selected randomly. So starting from this model, I generate the probability, and then depending on the probability, I fish from this distribution of models, the one who has more chance to be reproduced, and I start mixing them a little bit, or changing them with a mutation operation. So I will have a new generation of models, starting from this, that you see are getting closer and closer. And then for each one of these models, I again calculate the dispersion curve. I will calculate for each one of these models, again, the misfit function, and so on until I get models that are converging and becoming more and more similar after many of these iteration and generation. If you leave it fully open, this selection procedure and mixing of model, it can take a long time before that the model is that the solution is converging. So you can test really a large amount of data. So a good a way to speed up the procedure, it's what we call elite selection. In this case, with elite selection, what we are doing, we say, okay, we change all the models, but we keep in the next generation also the previous best model. So the best model that we had in the previous generation is surviving without any change in the next generation. This is, of course, one possibility, but the risk is, again, that maybe we are not exploring enough the space of the solution, and we are stuck, like it could happen in the linearizing inversion, in a local minimum of the solution. So to avoid this, then there is also another operation that is used that is called dynamic mutation. So if we see that after some iteration, the best model is always the previous one and the solution is not changing, then the probability of having a mutation is increased in order that we try to generate more different model to explore a different part of the solution volume, and then to restart maybe the search in a different area of the solution. So this is really done to avoid a premature convergence of a solution in a local minimum. So this operation is repeated until we found really a good solution for the model. Okay, these are the two methods that you can use. And both methods, linearized or non-linearized, like in this case, full nonlinear inversion, are used for the H over V inversion and also for the dispersion curve inversion that we will see later. Okay? Questions about this part? So
Yes.
now when we will talk about inversion, this should be enough clear, I guess.
Yes, I have one question.
Yes, tell me.
Okay. Okay, the selection was a curiosity.
Yes.
The selection of the initial model, whether it's for the linear inversion or the non-linear one, which one is there a criteria to select that initial model?
As I told you, a little bit on the criteria I told you before on the wavelength to define maximum and minimum. Another way could be, as I told you, to calculate the wavelength from the dispersion curve. No? At each frequency, you can calculate the wavelength. You can divide the wavelength for 2, and this is becoming, therefore, the depth of investigation. And at that depth, you assign the phase velocity multiplied, for example, for 1.05, which is the ratio between Rayleigh wave velocity and shear wave velocity. If you plot this with depth in the epsilon direction and the velocity in the x direction, you have an idea of a reasonable velocity profile. So you know the velocity will be in this range. So if you then make of this curve a layered model, you can use these directly in the linearizing version. Or you can just define a range of values and the range of depth for each layer spanning around the values of this curve. And this will be your, let's say, starting a range of models of velocity and thickness for the uh, genetic algorithm inversion.
Yes.
Is it clear, this?
Yes. I was
okay. So you have an idea of the range that you can span, and then you will let the algorithm to play and to look for the best solution. This could be the point. Okay.
Yes, I was remembering some procedures that I used to see from my colleagues, from my master degree colleagues, that they use the Marmouzi model, but I think that was pretty much used for seismic reflection data. So
I didn't get which model you mentioned.
Marmouzi model, like a distribution of velocities with a given structural with a given
depth.
geological, exactly. So I was
exactly
also,
this is also a possibility, of course, but you have always to take into account. In this case, I was telling you something without any extra information on the stratigraphy, for example.
Exactly.
No? Or on the material. Of course, if you have also information on the material and you know what is the range of velocity of this material for that area, because you know also sands or clays or gravel can have a very large range of velocities. So you have to be careful also in this. But if you, of course, you can use this as indicative information to set up your starting model, of course.
Great.
Okay.
Yes. Thank you.
Any other question?
I had a question.
Hi, Shoaib, tell me.
Yeah. So when we are doing the inversion, we are calculating the difference between the observed and the calculated from the assumed model. So we take the phase velocity versus frequency branch as just one branch, which is either for fundamental or some other.
You go more far away. You can do two things. Okay, you can have an inversion if your curve is only for the fundamental mode, for example. Then you can make the inversion only for the branch for the fundamental mode. Or you can also perform the inversion using different modes. So again, I was simplifying here, that's clear. But if you have information on different modes, of course, you can also find a model that is fitting the different modes, for sure.
Okay.
The problem can be in cases where the distinction between the modes, it's not clear. So like if the energy of the different modes is coming at similar time, so you cannot separate it. And this is a case very typical when you have inversion of velocity. And in this case, the inversion, maybe I can find the slide, let me see, is done not considering a single mode or different modes, but considering what is called the apparent velocity. So we generate a dispersion curve that is a mixing of modes, and the modes are based on their, and the shape of this curve is based on the energy of the different modes. Okay? We wait on the energy of the different modes, and we can see a curve that is mixing the modes all together. And that's what is very often done. I'm just trying to find a figure, but we will see it later when we will discuss about the dispersion curves. But just for your curiosity, here, for example. You see, this is the case where the fundamental mode is dominant. This is the case where, for example, the modes are mixed and the dispersion curve cannot distinguish the different modes. So you have to give this possibility. And also here, you see, you have a mix of fundamental and higher modes. So this is accounted for in the inversion. So you can tell the inversion also to apply this point. This is also very important where you have very thin, for example, sedimentary cover and very strong impedance contrast. We had some cases in Italy like this. And what is even happening is that the predominance of the higher modes, like here, it's not in the high frequency like generally we expect, but it can become also dominant in the low frequency part. And if it's not recognized, this can lead us to important errors in the model that you can obtain from the inversion. So it's really an important point to take into account. So you can have all the cases. Very often when you work with seismic noise, you are not really able to separate the different modes, the different branch of the different modes. And then you work more in calculating an apparent dispersion curve that is calculated considering, like here, the velocity of each mode weighted on the energy of the mode itself. Okay? Did I answer to your question, Shaib?
Yes, yes.
Okay.
So, yeah, thanks.
It's clear?
Yeah, I think you will go in the details later, but for now it's
Yes, a
clear.
little bit. Yeah.
Yeah.
Okay. So if we come back now to the standard H over V measurement, so now we know a little bit about inversion. So I hope also the people who never heard about it as some ideas now about it.
Yes.
And okay, and we will see it again when we will discuss also the dispersion curve and also how to invert together for H over V, for dispersion curve or love, and even love and Rayleigh waves altogether. So this is just an example now of inversion of H over V. So you see, we have observed H over V. In black, we try to calculate an H over V for a standard profile. We did it here using different methods. And we had some constraint. We are again in the area of Cologne that I showed you before. We had some constraint on the thickness of the sediments that we obtain from the relationship obtained using Borel data. So using this, for each point that you have in the map, we were able to calculate a shear wave velocity profile. And then what we have done, we made a simple interpolation between these many 1D profiles, and we obtain a sort of pseudo 2D section. And what you see here is the results of this pseudo 2D section obtained over 30 kilometers simply from inversion of a single measurement of noise. And to us, it was quite impressive to see how good the cross-section and was representing also the features that we knew from independent geological data, where they estimate, for example, for the quaternary layer, a thickening in the direction of the fault and so on, things and features that you can clearly see also in these cases with totally independent data. So of course, the point was, if we have some independent information, and you have, in this case, H over V, you can also retrieve the 2D underground structure, or even the 3D underground structure of the basin. And this can be very useful if you want then to make a numerical simulation of shaking. So I can assume that there is a fault somewhere here generating an earthquake, and check the propagation of waves in a basin to simulate what would be the effect of an earthquake in the area, especially in areas where you don't have a lot of earthquake recordings. The numerical simulation can become a very useful tool for obtaining important information in case of large earthquakes and very impact. And you see very nicely here how the basin is thickening in this direction, especially where the velocity, the small velocity layer is increasing in this direction, showing a very large increase also of the thickness of a sedimentary of a sedimentary cover, and mainly in red you have hard rock, bedrock. So all these complicated features can be then obtained. And the good point, if you are careful enough and if you are including also extra information, is that with simple tools like this, it's possible to generate a good model for a basin, at least good enough for what we are using in seismology in general, for at a relatively low cost, and especially also in urban areas. So in areas where other geophysical approach can be difficult. So this is offering a new opportunity. Another important point for the noise measurement is certainly the analysis of also the structure. So as I mentioned, we are very much interested in understanding the frequency of shaking on the ground, because if this is similar to the frequency of shaking of the buildings, we can have a resonance and therefore damage can increase. So very often we use noise measurements also inside the structures to estimate, let's say, some parameters related to their dynamic behavior. So for example, the frequency of oscillations of this structure. Of course, the behavior of a building during strong shaking will be different from the behavior that we expect during the small shaking induced by ambient vibration and by by this seismic noise. But at least they can be very useful in fixing some of these parameters for the starting behavior, let's say, of a building also during large shaking. Then we expect that the parameters will change, but at least using these methods, we are able to fix the starting parameters. So for example, these are measurements we have done many years ago here on a building that was an hospital that is made mainly of 3 blocks, let's say in this way. And also the engineers, they were making with us measurements here, they didn't know exactly from the design if a building was behaving like a unique block shaking altogether. I think Chiara knows this problem quite well on what I'm talking about. Or like 3 separated completed blocks, or like 3 blocks linked, let's say, like by springs. So we made measurements in the hospital inside and outside. The first thing that you notice is that the colors are representing the measurements made at different floors. And you immediately see that, at least for the first frequency, there is a clear evidence of increasing of the shaking when you go to the higher floors, which is quite something that we expected. While outside, it's clear that there is no effect or very small effect of the building structure on the ground. So this building, we could retrieve its frequency of vibration very well. While this is important, because we identify the frequency of vibration univocally, but simultaneously, our engineer colleagues made dynamic simulation of a structure for the different kind of models that they had in mind. And we compare the results of their modeling in terms of frequency of oscillation of the structure, of course, with the results of our observation. What we observed was that there was only one model fitting reasonably our observation, and this model was the model considering the free part of the structure like link, as I said, by link by springs in the separated joints. And we observe a quite good coincidence of this value. You see they observe 1.78 for the first frequency, we got 1.8. We didn't observe a second frequency, 194, probably because at the time we were smoothing too much the spectra. There is a reasonable value on the east-west direction of 2.34 and 2 in our case, 2.78 and so on between observation and simulation. So at least we could fix that the best model was certainly this, and that we had to use this model then for dynamic simulation in case of strong motion. So this is another way to use a seismic noise, also to get information, at least the resonance frequency of structure. Recently, and I will show you later, we are also doing more. We look at the wave propagation inside the structure using more advanced method, a little bit similar to what I show you for the boreholes. This was also used, the approach to study a very complicated structure like the Cologne Cathedral. I show you this example because this is a very fascinating example. This is an historical cathedral, which it's nearly impossible, at least that's what the engineer colleagues told me, to model, because it grew up in centuries with a very complicated structure that would be nearly impossible to reproduce in a reasonable numerical simulation. But nevertheless, we have made measurements in different parts, especially of the main body of the cathedral. The towers have been already studied by other colleagues. And we had surprisingly good results, for example, showing some differential movement between the Navy and the Choir that in case of large shaking event could have brought some damage to the structure. So we couldn't, let's say, use these values for refining the dynamic modeling of the cathedral, but at least we could identify some critical points that were of particular interest for the colleagues in order to define possible actions in order to retrofit the cathedral or to take action to mitigate damage in case of a large earthquake in the area. Okay, these are the main points for what regard the usage of H over V. So we saw we can use it as a sort of tool for estimation of the fundamental resonance frequency of a site directly. We saw that we can use H over V as a sort of exploration tool combined with other information coming from a sample from borehole to define the thickness of the sedimentary cover, so to have a good mapping on the basin. We saw that it can be used under some constraint, again, in an inversion procedure to obtain the shear wave velocity below the site, if we are able to solve in some way the trade-off problem between velocity and the thickness of the sediment. And then we observe also H over V and noise measurements can be a useful tool not only for the ground investigation, but they can be also useful tool for obtaining important information also on the behavior of building structure. Nowadays, we are not working, or we try to work not anymore only on the structure on the ground, but we really like, when possible, to get information simultaneously about noise on the ground and in the structure in order to study both the systems, let's say, in a unique way, in a harmonized way. We want to study how waves are behaving in the soil, in the structure, and how the two things are, let's say, playing together. So this is our main aim that we have at the moment, especially when we look at single structure, a single measurement. The next point that we will start next week is always how to study the underground structure in order that we can improve our models. And then we can make, like we mentioned several times, numerical simulation of ground motion to obtain a good estimation of what could be then the impact of an earthquake on a certain structure. We will mainly see linear arrays that are mainly working with active sources. So it means we are playing on the ground many sensors. We activate a sort of source. We are recording a signal in the ground on many sensors along the line, and using this information, mainly I will show you example of how to calculate the dispersion curve, and then again in a dispersion how to obtain a soil velocity profile. If we are not using an active source, mainly we use again seismic noise or ambient vibration in array configurations. So we will place the instruments on the ground and we will study how the waves are propagating along this array, this 2D array, in order to estimate the dispersion curve and to invert it to obtain the shear wave velocity profiles. All this information then are used to characterize a site, which is a major importance in seismic hazard estimation and also in seismic hazard and risk in real-time calculation, but this will be the last part that we will see. Okay, any question about what we have seen till now? So clear? No question? Not even from the engineers? So I start fearing that everything was unclear, if no question. If everything is unclear, tell me, we go back tomorrow, next time. Don't be shy. Okay.
I have a question, but it's a kind of a query. I was just wondering if the analysis we perform through the noise and using the noise data, it can be considered the same as we are working on the earthquake data, like both are different and have some deformation is mostly related to frequency dependent.
No, it's not a question of really frequency dependent. It's more a question of amplitude of shaking or large shaking.
Yeah, in any kind, yeah.
So of course, when you will have large shaking, I don't know if you refer to soil or to a building or to both.
Yeah.
But in both cases,
both.
in both cases, you can have a large nonlinearity. So when you will have a large ground motion, soil start behaving non-linearly. So the response can also change significantly, even if in some ground motion parameters that are using seismic hazard, sometimes the effect of nonlinearity is not so clear. So there is also a discussion, some of the guys who are here following lectures working in Orbesis, they are exactly dealing with this problem. How clear can be this effect? Depends strongly on the parameter that you analyze and the frequency content and so on. In the building is the same for different reason, of course, but also the building response can be completely different when you start having large shaking, nonlinearity, and then even worse when you start having damage to the structure at different level. So this is a clearly different behavior. But as I said, even to start with simulation, you have to have a good knowledge of the starting parameters, any stiffness or other parameters, so damping of the structure. And very often, only looking at the design of the structure the model is not really adequate. At least in my experience in the past of working a lot with engineers, every time we try to make numerical simulation of a building, starting from the design of a structure and then comparing the data, the numerical simulation also for small motion with the observation, we observe nearly always discrepancies. So it was good to have also small vibration measurements who could fix, let's say, the parameter better, at least for the numerical simulation, and then of strong motion, and to get probably more realistic estimation of the dynamic behavior of the building. I think, I don't know if Chiara is here and she's working a bit on this, agree on me, but that's mainly my experience.
Okay.
I agree, I agree.
Okay, thank you, Chiara.
Okay.
If there is no other question, we can update to the next week. So I wish you a good continuation of the week, and see you next time then.
Okay.
Bye-bye.
Thank you. Bye.
Welcome.
Thank you.
Thank you.
Ciao.
Bye.
Thank you. Bye.
Bye-bye. Bye-bye.
Yes.